All right, let's get going here. So as far as our schedule is concerned, we are where we need to be. But we do have a problem with this exam too, right? We talked about that. Still haven't figured out. We only have what? 1, 2, 3, 4, 5 class meetings and then a final. So we only meet like 6 times total. One of those is, well, 2 of those are supposed to be a test, right? So that would mean we only have 4 class meetings of lecture. So, yeah, I mean, summer 8-week Cal 1. This the problem we run into is where do we put things, right? At what point do we have a test? So, and we lost that holiday, July 4th. So let's get through today, and then just remind me at the end of class, let's talk about this exam, all right? Where we're going to put it. Are we going to leave it here?
Next week.
You know, do we want to have it next week? Yeah. We'll talk. All right, we are starting chapter 4 today. And chapter 4 is called Applications of Differentiation. So we're going to see some of the things we can do now that we've established derivatives. We have done one type of application. We've done the related rate problems, right? Those word problems that nobody really liked. And when we did those, we were using implicit differentiation, right? Here, we're just going to use our normal derivative, right? No implicit, and we're just going to see what the derivative actually can help us do. So the first section here is called maximum and minimum values. Let me make this a little bit bigger. This might be too big. Maximum and minimum values is the title of the first section. So the good thing about this section is that it's very visual. So the idea is pretty easy for most students to understand. It's that there's a lot of language in this, so we have to make sure that we understand these definitions we're going to see. All right? So the first definition that we have here is what's called the absolute maximum or minimum values. So first, the definition. And when you read this the first time, you're like, okay, that doesn't make a whole lot of sense. But then I'm going to have something visual to go with it. All right? So let's read through it first. If we're given some curve f, so we're given some function, and it's defined on some domain, so the domain might be everything, it might be just an interval, but let's say that that's given to us, right? So got some curve here, right, f, and then, you know, it's defined on some domain, whatever that is, I'll call that D, right? Then it says here that some number c in D, so that there's some value here, C in D, that when you look at that number C plugged into the function, we're going to call that y value, okay? The distance from here to here, that's f of c. That's how tall the function is, or how high that point is, or how low it is if it's below the x-axis, right? That value right there is going to be called, f of c is called the absolute maximum value of the function f on D if f of c is greater than or equal to f of x for all x in D. Okay, so what does that mean? That means that if I were to pick another value, to say that that's an absolute maximum would mean that if I picked any value near this one, okay, anywhere in here, any x value I ever want, that point would be the highest point compared to all the other points. Now, from my picture, this is not an absolute maximum, is it? But can you imagine what it would look like? Probably the top of a hill, right? Would be where you would have an absolute maximum, because all the points around it would be below it. An absolute minimum is the reverse, where that point's not the highest point, not the biggest point, but the smallest point. So let's just look at a picture. So look at this right here. All right, look at that curve right there. Do you all see a maximum, an absolute maximum value somewhere? Yes? Looks like right about here, right? Do you all agree that that would be the highest point on the entire graph? So the absolute maximum value would be whatever that value is right there, okay? That would be the absolute maximum. And then wherever this happens, right, is just where it occurs, right? So that would be the C value. This would be the C value that gives us that absolute maximum. Do you all see an absolute minimum? Yeah, looks like right here, right? And again, the minimum value right here, whatever that is, that would be your absolute minimum. Put abs min. And then this would be the value where it occurs, right? That would be the C value where it occurs.
So C is always in the X.
C is always the X where the absolute max or minimum occurs.
Is the absolute minimum and max the Y value or the
It's the Y value.
So it's not like
It's not the point, it's the Y. It's this distance from here to here, that's your absolute minimum. Whatever that Y value is, that's your absolute minimum. This Y value up here is your absolute max. Okay, good? All right, let's get back up to the definitions of another definition. And this is a weird definition because it almost looks exactly like the definition I just gave you. So this says, all right, we're given a curve again, right? F. It's defined on some domain D, okay? And then there's some number C inside that domain. Everything there is exactly the same. Now, it's the definition. F of C is called a local maximum value, not an absolute maximum value. A local, that's the difference. If, of the function on D, if F of C is greater than or equal to F of X, that's the same exact definition. But right here it says for all X what? Near C. What did it say before? For absolute maximum, it said for all X in the domain. For all X in the domain. This is saying all X near C. That's the only difference between those two definitions. And this is where we get into this gray area. Remember we had that conversation about, like, are we close to one another? Are we close to SeaWorld? Are we close to the sun, right? Near is relative, right? It's a relative word. So in this class, we don't get into that in any deeper detail because we can really go down a rabbit hole, there. So for near for us is going to be, I think, what most of us logically would think of as near when we see a picture, when we see a graph. So let me keep going here. So you are called the Y value. Okay, the Y value is called the local maximum value if that value is greater than or equal to all other values near that value C, and then local min if it's smaller than all values near it. And then if the function is defined on a closed interval. Okay, so if your function is actually going to start at a point, end at a point, the endpoints are always considered local maxes or mins. All right, let's take a look at a picture. There's a good one. All right, let's start with absolute max and absolute min first. Does this function have a highest point somewhere? Where is it? At the right endpoint, right? This right endpoint would be the absolute max. Now, when we say absolute max, again, we're talking about the Y value, whatever that Y value is, right? And where it occurs, I don't know, that's some value that I could maybe figure out, right? That'd be an absolute max. Does it have an absolute min? Where? Looks like about -5. So right here at the bottom of this little valley right here, that point's an absolute min. That's the lowest point on the graph. That's the highest point on the graph. All right, now let's talk about locals. Locals only have to be, let's talk about local max first. To be a local max, you only have to be the highest point near that point. So do y'all see any local maximums? Where?
Is it that one that
Tell me when. Right there?
Yeah.
I agree. That is a local maximum. Why? Because if we just focus our attention right here in this little region, it's the highest point in that little region, that little area. So this would be, I'm going to put L max, is that okay? L for local. That's a local max, and the local max would be the Y value, okay, whatever that Y value is. All right? The left endpoint would also be a local max. Well, oh yes, you can have more than one, absolutely. So that's a local max as well, because why? If you're just focusing your attention here, it's the highest point in that little neighborhood. Yes. Right endpoint would also be a local max. It's also an absolute max, but this can also be referred to as a local max, because it is in fact the highest point in this little neighborhood. Do you see any other local maxes? So local min, let's talk about local mins then. So no more local maxes. We're good? Yeah, that's it. That's all of them. Why would this not be a local max? Yeah, if you look in this little neighborhood and just take any point to the left of it, it's higher, right? So to be a local max, you have to be kind of like the king of the hill, right? The king of that hill at least. Or you have to be the king of this hill, but this hill only has one side to it, right?
What did you say about local maxes can be absolute maxes?
Well, this point right here is actually our absolute max and our local. It can be, when you look at this, you can look at everything first locally, and then you can say, okay, what about just on the whole graph, what's happening? That's the highest point on the whole graph. All right, so this one we said local minimum, right? Local min, because it is, what? It is the lowest point in this little neighborhood, right? Do we have any other local mins?
Yeah,
Right there, right? Local min. Okay. Any others? What about the endpoints? Well, it's going to be one or the other. So you can't say that this is a local minimum because it would have to be the lowest point near here. And if I go to the right, everything's below it. So this is a max, local max. So that's it. That's all we've got. Okay? Geometrically, does this make sense? Okay, let's take a look at another graph. Let me make this a little smaller. There we go. All right, for this one, notice that this graph, well, I don't know if you can tell, but those ends of the graph are supposed to continue forever. So imagine that there's an arrow here and an arrow here. And let's talk about absolutes first. So how about an absolute max? Do you see a highest point on the graph? There is none, right? You can't tell me there's a highest Y value. Like if you try and pick a Y value and say, oh, that's the highest, I can always find one higher. Why? Because the arrow is implied to keep going forever, right?
Can you say infinity?
The local max has to be a number.
Oh, okay.
Good idea, but for maximums, for absolute max and mins and local max mins, we can't have infinity as an answer. So we're going to say here, no absolute maximum. All right? We have no absolute maximum. All right, what about absolute minimum?
Yes.
Yes?
Right there. Or like that.
Here, this one? Yes, that's our absolute minimum. And that's because it is the lowest point on the entire graph. All right, let's talk about the locals. So we don't have endpoints here, do we? So we don't even need to think about endpoints. What would this be? Local min? Local max? Local min? Anything else? That's it. Okay? Any questions?
So every absolute is also going to be a local.
What do y'all think? What do you think? Yeah. If you're an absolute min, then it's got to be a local min. If you're an absolute max, or if you have an absolute max, it has to be a local max as well. What about this? I'm going to make up my own real quick. We'll start it here. We'll end it here. There. Horizontal line segment. Let's start with absolute. Let's start with absolute. Show of hands. Absolute maximum, yes or no? You think so? Let me put a value here so that we can actually talk about it. Let's say that's 5, okay? You think so?
Is this the highest point on the graph?
It is the highest point on the graph. Let's go back to the definition for a second. The definition is what's going to tell us here. The definition says for absolute max to be an absolute maximum, it's some y value that is bigger than or equal to all the other values on the function. If that equal was not underneath, then we would not be able to talk about this being an absolute max. But according to the definition, the value of 5 is an absolute maximum, right? It is greater than or equal to every other value in this function. So I could say for this problem, the absolute max, right, is 5, right? Because it's the y value. Does it have an absolute minimum? Yes. What is it? 5 as well, because in the definition it's got to be less than or equal to. So your absolute minimum is also 5, right? And how about local? Did local have the same thing or not? In the definition, did it have greater than equal, less than equal? Yes. It did, didn't it? It's greater than or equal to, less than or equal to, which means that we have local maximums and minimums everywhere, right? Every single point on here corresponds to a local max and a local min. So this is just a weird example, all right? Just to kind of show you, like if you're just following the definitions, you've got a situation where your absolute max is the same as your absolute min, and they actually occur at every single one of these points. So I don't want you to get into this idea that if you have something like this, that if you have an absolute max, it can only happen at one place. You could have a graph that does this, goes back up. These two could be the same height, right? And then your absolute max is just whatever that height is, and it happens at 2 different places, right? Okay. Let's continue. I'm going to close this one. This is an example right here. Let's just point these out. Do we have an absolute max? Yes, right? This point and that point, right, both give you the same y value out, don't they? So the absolute max is whatever that y value is. How many different places does it occur at? 2 different x values, right? This x value gives you that absolute max. This x value gives you that absolute max. Same thing with min, right? Absolute min, 2 different places. And then locals, let's just call them out. What is this point? Local max. Local min. Local max. Local min. Local max. Right? Like I said, it's very visual, so most students do okay with this. All right. So that's just the visual part. Now we get into like what, I mean, ultimately, okay, where we're headed with this is that if I were to give you a function algebraically, y equals blah, 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 I give you some function, it would be nice if we could find those points, right? Wouldn't it be? If we could find like these peaks and valleys on a function. If you go back to college algebra, we know how to do it, right? I'm going to go off topic a little bit here. How many of you remember this from college algebra? That if you're given a quadratic function, right, which is a parabola when you graph it, that it either opens up or down, right? Depending on that value of a. So it either goes like this or it goes like this, right? And this point right here and this point right here in college algebra, we call that the vertex. Remember that? And that would be an absolute minimum, wouldn't it? And this would be an absolute max. Or you could say this is the local minimum and that's a local max, right? But in either case, we are given a formula, aren't we? Do you remember this formula? To find this point, we call this point HK. Right? Do you remember HK? And there was a formula for it. Anyone remember what H is? Did you write? There's a formula. Anyone remember what it is? Negative B over 2A. Good. Negative B over 2A. And then to get K, all you have to do is take that answer, whatever you get here, and plug it into the function. That'll give you the K value. So this X and Y coordinate of this vertex, either for this case or this case, can be found using this formula. Remember seeing that in college algebra at some point? Okay, so we've done this before, okay? We've done this before in college algebra, but this, we only could do this for parabolas, all right? Once you get to a higher degree polynomial, we didn't have a way of doing it. We would try and graph them in college algebra. We'd try and graph them, and we would find where they hit the x-axis. We would talk about this multiplicity thing where it like either bounced off the x-axis or crossed through the x-axis. Depending on your professor, you might have talked about how many turns you have and all this stuff, but we never tried to find the actual highest points and lowest points, all right? We will here, okay? That's what we're going to do with calculus, all right? So that's kind of where we're headed with this. So before we can do that, we need to establish some theorems that allow us to do what we're going to try to do. So the first theorem, and a theorem I've said before is basically a mathematical truth, right? Based on our logical system, this has been shown to be true. All right, the extreme value theorem says, if f is continuous, all right, what does it mean for a function to be continuous? Tell me, and like if you're trying to explain it to a grade school.
You can't lift your pencil.
You draw without picking up your pencil, right? Okay, so let's say we have a function where you can't pick up your pencil, and it's defined on a closed interval. Okay, so I'm going to give you an example next to this. I'm going to have a function that starts at A and ends at B. It's defined here, and over here I'm going to make it a different value. It could be any value I want. I'm just going to make it that one, all right? So it says if f is continuous on a closed interval, that means I need to now connect those two dots without picking up my pencil, right? So I'm going to go ahead and do that. And I'm going to just make sure. Can I do that? No. Why not? It's not a function, right? Fails the vertical line test. So I still have to be a function here. But I can do whatever I want there, like that. This theorem says if you have a continuous function on a closed interval, then your function attains both an absolute maximum value and an absolute minimum value somewhere in that interval. It's just saying that you're guaranteed to have a highest and lowest point. It's impossible to not have a highest and lowest point, as long as it's continuous on a closed interval. Do you all agree with that theorem? Does it seem reasonable to you? Yeah? I have a couple of examples here. So can you all see these 2 points? They're right here and right here, right? I'm going to connect those two together and show you that we're going to have an absolute maximum. So first graph I'm going to draw is that right there. Is that a continuous function defined on a closed interval? Yes? So I should have an extreme value. There they are, right? It went up and curved and came back down.
Oh.
It just kind of went up a little. So this is the absolute min, absolute max, right? Okay, so that verifies the theorem worked, right? Okay, here's another one. That's continuous on a closed interval. Absolute min, absolute max. See, the theorem says there's no way to do this without getting an absolute max and absolute min. It's guaranteed by the theorem. Here's one. Here, I'll try and be tricky. Straight line. Well, your two endpoints, right? Absolute min on the left, absolute max on the right. How about this one? It's not continuous. Okay, so I can't use the theorem, right? The theorem only applies if I have a continuous function. I drew one that was not continuous. And this actually goes up forever, right? So you could not say it has an absolute max. So you're like, wait, the theorem says I have an absolute max. Well, it's not continuous, so you throw the theorem out, right? Yeah, this one does have an absolute minimum, but the theorem guarantees that happens if you have a continuous function. It may still happen, even if it's not continuous. Okay, I'm going to skip Fermat's theorem right now, and I'm going to state it again. And the reason why is if I give you this theorem, it's going to confuse you. But it's in the book, so I put it in my notes, all right? I'm going to restate it after I state the following. We have a new definition, and this definition is going to be extremely important as we move forward, all right, in the next few sections. It's the definition of what's called a critical number, okay? Critical numbers. A critical number of a function, right? So if somebody gives you a function, right? Any function, and they say, hey, what are the critical numbers? This is what they are. A critical number of a function is some number c in the domain of f. It has to be in the domain of the function itself, all right? So if I have, like for example, I have a function that's only defined between, let's say, 2 and 7, you could never get an answer where you tell me that the critical number is 10, because the domain of this is between 2 and 7, all right? Your critical number must always be in the domain of the original function. But what is a critical number? It is a number c, some number, that when you plug that number into the derivative of that function, you get 0. Or you take that number c and you plug it into the derivative, and that derivative doesn't exist. Remember, the derivative is a limit, right? We talked about this last class, how the limit was the heart of calculus. I drew that real pretty heart, remember that? So the limit gave us the definition of the derivative, right? So if I plug a number into a derivative and I get something crazy, we would say that that derivative doesn't exist. So any point, in summary, a critical number is any number that you can find that either makes the derivative 0 or the derivative not exist. And this is an or, not an and. It's one or the other, all right? Let me do an example. I don't normally do an example right here, but let's go ahead and do it. Let's take, as an example, find the critical number slash numbers, because it could be more than one, of the function f of x. And let's just go simple here. There we go. All right, so there we go. I'm trying to find the critical numbers of that function. So what I'm going to do is I'm going to just figure out two different things. First thing I'm going to do is I'm going to ask myself, when is that derivative equal to 0? And the next thing I'm going to ask myself is, when does that derivative not exist? Right? I'm going to take the derivative of that, and then I'm going to set it equal to 0. And I'm going to take that derivative, and I'm going to analyze it visually, and I'm going to see if it ever doesn't exist. So I need the derivative, don't I? So let me go ahead and take derivative over here. Just some scratch work. The derivative of this should be an easy one for us, right? Minus 12x, right? 3x squared minus 12x. That's our derivative, right? So let's go find this first thing. Let's figure out where that's 0. So I take that derivative, right? And I set it equal to 0. And now I solve this equation. So up to this point in this class, when we've been learning to take derivatives, you remember how I've been telling you, like I've been trying to stress to you that we get the raw derivative, but at some point we're going to have to do something with that derivative? We have reached that point where we're going to have to do something with it, which means there's going to be algebra involved, more algebra. In this particular case, this derivative, setting it equal to 0, I have to solve this equation, right, which is a quadratic equation. And I'm now going to hope that you remember how to do things like this, right? How would you all solve this one? What would you do?
Take the x out.
Factor GCF. Factor GCF first. They both have 3x. And that leaves you with x minus 4, right? And then you set each of those factors equal to 0. The zero factor property is what it's called, but yes. It's called different things. So zero product rule is, or product, did you say rule? Yeah, same. You're referring to the same thing. So you set each factor equal to 0. Divide both sides by 3 there, you get x is 0. And over here, you divide, or not divide, you subtract 4, you get x is 4. Okay. Are those critical numbers for this function? Yes, so long as they are in the domain of the original function. Are they? Well, we never talked about it, but what's the domain of this? All real numbers. Why? It's a polynomial function. It's a polynomial function from college algebra, and all polynomial functions' domains are all real numbers. We are going to have problems, other examples in the class, where our function is going to have some sort of domain restrictions, and we will have to check these. Every single time we have to check to make sure it's in the domain. Is there a question?
So does that mean that that's not going to have an absolute minimum or maximum?
No, I've not said anything yet about, all I've done is define what a critical number is, and now I'm showing you how to find them. Fermat's theorem is going to allow us to now use this for something. So hang tight, it's coming.